Okay, so today we're going to focus on drawing Lewis structures, and we're going to use the Lewis structures to find out more about the given molecules. So we're going to follow 3 steps today. The first step will be to draw the Lewis structures for the following molecules. And a Lewis structure is a visual picture of the bonds and valence electrons that make up a certain molecule. And then our next step will be to explain how to find the partial charges and bond dipoles, which we can find by looking at the electronegative values of the atoms in the molecule. And then our third step will be to explain how to find the net molecular dipole, which we can find by looking at the molecular structures of each molecule. So the first molecule we're going to look at is SO3. And we're going to draw the Lewis structure first. So the way that we do that is first we need to figure out how many valence electrons are in SO3. So we're going to look at the periodic table, and we're going to find sulfur, and we see that it's in this column. So we're looking at the second number. It has 6 valence electrons. So we're going to write that, 6. And then we have 3 oxygen atoms in this molecule. So we're going to find oxygen. It's in the same column. And oxygen also has 6 valence electrons, but there's 3 oxygens. So we're going to have the 6 valence electrons from sulfur plus the 6 valence electrons of oxygen times 3, since there's 3 oxygen atoms. And that equals 24 valence electrons. So next, we're going to start by drawing our Lewis structure. And how we start is first we need to figure out which atom has the lowest electronegativity value, and that would be sulfur. So sulfur goes in the middle, and then we will draw the 3 oxygens around sulfur. And we're going to go ahead and connect all of these atoms with a single bond in between all of them. And then once we have those drawn, we can see that we have a single bond is made up of 2 electrons, 2 valence electrons. So we have 1, 2, 3 single bonds times 2 is 6 valence electrons. So we're going to subtract 24 minus 6, which leaves us with 18 valence electrons. So we still need 18 more electrons on the structure. And we'll go ahead and draw those around our outside atoms, which are the 3 oxygens. So we'll have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then 1, 2, 3, 4, 5, 6. And so we're going to make sure that we have a total of 24 valence electrons on this Lewis dot structure. So we're going to count the pairs of electrons. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 12 times 2 is 24. So we have the right number of valence electrons, but then we need to make sure that each atom in the Lewis dot structure has an octet. So all 3 of the oxygens have 8 valence electrons around them, but the sulfur is missing 1. So how do we fix that? Well, we can move a non-bonding pair from one of the oxygens onto the sulfur to make a double bond. So we can go ahead and move this pair here, right in here, to make a double bond with sulfur. So these will disappear from the side of the oxygen. And so now all of the atoms are happy because they all have an octet of valence electrons. So now that we have our Lewis dot structure, we can look at the partial charges and the bond dipoles. And so in order to figure out the partial charges, we have to look at the electronegativity values. So we have sulfur and oxygen. And sulfur's electronegative value is 2.5, and oxygen's is 3.5. And so since oxygen has the highest electronegative value, it is going to have a partial negative charge. All 3 of them will have a partial negative charge. and then sulfur will have a partial positive charge. And so once we have our partial charges, we can go ahead and look at bond dipoles. And bond dipoles basically show the movement of electrons toward the atom with the highest electronegativity. So we're going to locate our partial positive charge, and we're going to draw the tail of the dipole, and then the dipole is going to be going towards the atom with the partial negative charge, because that's where the electrons are flowing. So we can do that for all 3 atoms, and those are bond dipoles. And so now that we have our bond dipoles, we can go ahead and try and find the net molecular dipole. So looking at this structure, we see that it has 2 single bonds and 1 double bond, and which is 3 domains. And so this molecule has a trigonal planar molecular structure. So we're going to go ahead and draw that down here, and we'll put the sulfur in the middle, oxygen, 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 and then we'll draw out our bond dipoles. And this molecule is nonpolar because all of the domains are the same. We have 3 single bonds on the central atom, and so the bond dipoles cancel. So our molecule is nonpolar, and so there's no net dipole. So we'll move on to our next molecule, OF2. We have the right Lewis dot structure here, and so we'll go ahead and start with our partial charges. So we have oxygen and fluorine, and their electronegative charges are, let's see, oxygen's is 3.5 and fluorine is a 4.0. So fluorine has the highest electronegative charge. It will have our partial negative charge, and oxygen will have our partial, I'm sorry, I'm really bad at drawing those little symbols, partial positive charge. And then we can draw our bond dipoles. So we find the partial positive tail, and it goes towards the partial negative. And then we'll go ahead and draw our molecular geometry structure. So oxygen has 4 domains, but we're not looking at the non-bonding pairs. And so we have oxygen, and then we have our 2 fluorines, and then we'll also go ahead and draw in our 2 non-bonding pairs to show the differences, and our 2 bond dipoles. And so because all of the domains coming off of oxygen are not the same, we have 2 single bonds and 2 non-bonding pairs, there will be a net dipole, which you get by adding the 2 bond dipoles that you have. So the net dipole is going to be going down, and again, and the molecular geometry is bent. And again, you get a net dipole because all the domains are not the same. Our next molecule is BeCl2. So again, we have our Lewis dot structure. The electronegative charge on beryllium is 1.5, and the electronegative charge on chlorine is a 2.5. So highest electronegative charge, chlorine gets the partial negative charge, and then beryllium will get the partial positive charge. And our bond dipoles go from partial positive, partial negative. We will draw our molecular structure. Pretty simple one. Oh, and forgot to mention this. So, like I said before, normally in a Lewis dot structure, each atom should have an octet, but we see this one, beryllium, doesn't. beryllium is an exception, and it can have fewer than 8 valence electrons on it. So in this structure, it only has 4 valence electrons, which is okay. So here's our molecular geometry. It is linear. We'll draw our bond dipoles, and there will be no net dipole because, again, we have one single bond, they cancel. All the domains are the same, so there's no net dipole. Then our second to last molecule, CCl4, we have our right Lewis structure. Let's see. The electronegative charge of chlorine, again, is 3.0. Shoot, did I do something? Okay, sorry, I messed up on this one. Everything is right, I just messed up on the electronegative charges. So chlorine is actually 3.0 and beryllium is 1.5. So that's just a change there. Okay. Okay, sorry. Okay, and then going back to this one, so chlorine has a 3.0 electronegative charge. Carbon has a 2.5 electronegative charge, so chlorine will get the partial negative charges, and then carbon will get the partial positive charge. Here are our bond dipoles. And then our molecular geometry is a tetrahedral because we have 4 domains. So we'll go ahead and draw that. And then bond dipoles. And this structure is nonpolar because all the domains are the same, and so all of our bond dipoles will cancel, and so there will be no net molecular dipole. And then our last molecule of today is ozone, O3, and we have the correct Lewis dot structure, but we're not going to draw bond dipoles on this one. We can basically just look at the molecular geometry of it. And so if we have 4 domains, but one of the domains is a non-bonding pair while the other are bonding pairs. So we'll have oxygen, oxygen, oxygen. We have our non-bonding pair there. So our molecular geometry is bent, and since all the domains are not the same, this molecule will be polar. And so last thing I'm going to talk about is just common mistakes. A lot can go wrong if you don't draw the Lewis dot structures correctly. So that would be just make sure that all the atoms have an octet around them unless it's an exception, and just making sure that you have the right valence electrons on the whole complete Lewis structure, because if you mess up the Lewis structure, you mess up the whole problem. So I think that's it for today.